So I'm here to talk about non-uniform memory architecture. This will be maybe an introduction of what this is. It's been around for a while, so maybe people have experiences with it. Maybe people have good experiences, bad experiences. I'm going to share some of my experiences with it. So what are we talking about? Non-uniform memory architecture, short letter is NUMA. It's been a four-letter word in the Open Edge community for sure. This is something that we have been telling you from the Open Edge development community and the experts in the Open Edge community to avoid it at all costs. However, it's hard to avoid now. It's really hard to buy a server class machine that is not NUMA at this point. So I guess we have to take our head out of the sand and deal with this. And that's what we're going to try to talk about here today. Who am I? There's a lot of familiar faces here, but I'm Mike Furgal. I worked for Progress back in 1989 in development, and I left in 2022 to go join the Parmerton Foundation, whatever that is. If you know Gus, Gus is the head groundkeeper of the Parmerton Foundation, so I asked him if I could work for him, so I'm the assistant to the head groundkeeper at the Parmerton Foundation. If anybody in the US anyways has seen The Office, they'll get that joke. What's that mean? That means that I retired. Gus retired about 5 years ago. I followed him in April and I'm now retired, but I have the chance to come to Austria, see some old friends here and do this presentation. I'm very happy to be able to do this. And that's me in Mexico on my first week of retirement with my retirement hat. Okay, so non-uniform memory access is not new. Back in 1996, Data General, if you guys remember them, we had a really good working relationship with Data General. They used to run a Unix platform on their hardware, and they would come to Progress all the time and talk to us about their hardware and their benchmarking because they were selling a lot of DG hardware because of our Open Edge database and the application partners that have written applications on top of it. So they would come to us a lot and give us some hardware to play with. And in 1996, they came to us with this concept of NUMA. And we went, oh boy. And we tested our software on there and it behaved exactly as we expected. It would probably not scale well on the NUMA platform. NUMA had been a DG thing only and had really not been adopted by anybody else, so DG went away. We said okay, so we didn't really have to deal with it anymore, but it's much more common now, and I'll tell why in a second, but it allows for many CPUs on a system. If you don't have NUMA, you're locked down to a small system. It also allows for large memory. In large memory, we're talking about terabytes of memory. It's easy to get gigabytes of memory on a single chip. It's hard to get terabytes of memory on a single chip today. 10 years from now, it's going to be easy to get terabytes of memory on a single chip. But this NUMA allows you to scale beyond what single components allow you to scale today. So I don't know if you know this, but Intel has a hard limit that you can only have 4 CPUs on any Intel machine. That is a hard limit. That limit is not going to be overcome. It will actually never be overcome. This is what DG was trying to overcome back in 1996. So we're talking almost 30 years ago. They couldn't figure out how to overcome this limit, and we still cannot figure out how to overcome this limit. So what did they do? What did the hardware world do? They put cores on a chip. So now you have 4 CPUs, but you have multiple cores on that CPU. And that delayed the prospect of the world that we're in today. So now you have cores, you have a 4-core, 8 CPU machine, it gives you 32 CPUs. But what you can do with NUMA is now you can combine those to make a very big machine, like a 4-node 32 CPU machine to get 128 CPUs. So NUMA is the bundling of these 4 CPU machines into a single chassis. There's a high-speed bus that connects them, and there's one operating system that's in charge of all the nodes in a multi-node NUMA system. So what do you need to be aware of? You need to be aware of your IT people who get the big eyes saying, wow, for $30,000 I can get 132 CPUs. That's a flag. You don't want to be going down that path. What open edge application needs 132 CPUs? I can't even imagine one. I've worked on very, very big systems. Tens of thousands of users, tens of thousands of character shared memory users on a machine. It does not need more than 32 CPUs, no matter what the application is. So there's no need to get this 128 CPU machine. I can tell you I have one. Well, at Progress I had one. Our IT director said, got the big eyes, and they bought us a machine for our back-end database, and it's a NUMA machine. So we have to deal with all the NUMA consequences because of it. So beware of the notion that you can get these big, wide machines for low cost, because what it ends up being is a NUMA machine. So this is what it looks like. It looks like a cluster. So you have CPUs, or you have nodes, and those nodes have CPUs, 4 of them each, and they each have their own set of memory. And then there's a high-speed interconnect that connects them all onto a bus. So each one of them has its own bus. So if we think about how hardware is designed, and I know we're all software people here, but you need to know a little bit about hardware. There's a disk drive, there's CPUs, there's memory. Well, the CPU and memory are connected by a bus, and that bus is really, really, really fast. It allows them to almost operate, operating within nanoseconds to be able to fetch and stuff. But there's even more. There's also a cache line inside the CPU that moves memory from the memory chips to the cache line across the bus to the CPU. So everything needs to get near that CPU to be able to be operated on. So each one of these has their own bus. So you see that AMD one has its 4 chips of memory. It has a bus that's connecting that CPU to that memory. And then it has this high-speed interconnect, or high-speed bus, they like to call it, that's connecting the nodes together. So as we say here, there's a single operating system, and it behaves like a cluster if you squint. So it's 4 distinct nodes, 1 operating system across it. So what's the problem here? The problem is that when you're reading memory from one CPU and you're reading it locally on the CPU chip that's connected to that bus or that cache line, it takes a factor of 1 to read that. If you now instead on node 1 need to read memory that's on node 2, it needs to copy that memory from node 2 across the high-speed interconnect and bring it into its own L1 cache, and that's a factor of 3. So it's 3 times slower to read memory from CPU on node 1 to memory that's on node 2, 3, or 4. And that can be significant. And we'll talk about why that's significant. Does that make sense? Do you have a question?
No, I just thought you should point out that
oh, this is my boss.
All the CPUs can access all the memory in all of the other nodes. It's just slower.
Right. That's my boss, Gus. So I have to defer to him. Yes. What? Repeat the question? Repeat? Yeah. So Gus said his point was a point of clarification that all the CPUs have access to all the memory and all the other nodes. From the CPU standpoint, it just looks like memory. It has, and from the operating system standpoint, it just looks like memory. You have no idea if that memory is on node 1, node 2, node 3, or node 4. It's just a pointer in memory, and the operating system and the application does not know where that memory is. That was your point, right, Gus?
Yeah, well, that, and then if it's far away, it's slow.
Yeah, and if it's far away, it's slow. It's actually, it's called the NUMA quotient, which we'll talk about as well. The NUMA quotient is what's the cost or what's the difference between reading memory locally versus reading memory far. And it's typically 3 to 1. It's 3 times slower to read memory across a node.
That's optimally.
Yes. It could be worse, right? So it's typically 3 to 1. It depends on the architecture of the system. So 3 times slower to read memory across a node than to read it locally. Ready to move on? How do you know if you have a NUMA machine? Well, if you have many, many CPUs, you have a NUMA machine. On Windows, you can look in Task Manager and you can drill down, and I know this is probably an aged screen because Windows changes location of everything with every single operating system that they do, but you get the sense that in Task Manager, you should be able to go into View and be able to expand to see if you're on NUMA. If you're on Linux or AIX, because NUMA is available on AIX as well. How many people are running AIX, by the way? And you guys know that in 12, it's going away, right? Okay. You can run dmessage and grep for NUMA, and it'll tell you if you have a NUMA machine or not. If it says configuration not found, no NUMA. If you now get a lot of information, and I just took the first line that said, okay, I'm initializing stuff, then it goes on for pages about how it's booting up the NUMA environment, that'll indicate that you have a NUMA machine. Likewise, if you're on a machine, you can run a command called NUMA control if you have NUMA control. If you don't have NUMA control, you can just go yum install NUMA control. You don't need to have a NUMA machine to be able to run this command. If you have a NUMA machine, you run NUMA control -- hardware, and it'll tell you what your configuration looks like. And again, we'll talk a little bit more about this as well. If you run NUMA control and don't have a NUMA machine, it'll just say no hardware found. So what's important here? Affinity is what's important. So in that picture where you had those 4 nodes with their own private memory, if you were accessing memory locally, it's 3 times faster than accessing memory remotely. Wouldn't it be great if we could put memory on a single node and then guarantee that all processes run on that node? Well, by default, that doesn't happen. So the operating system has a scheduler, and that scheduler determines where each process is going to be running. So in simple terms, you might have 4 CPUs, and you might be running on CPU 1, and then your quantum or your time slice is up, and you are swapped off of CPU 1, and then when it's time for you to get back on the CPU, you might be on CPU 2. You're not guaranteed to be back on CPU 1. There's no mechanism to guarantee that. So you swapped off, and then you swapped back on. So as this says, a long-running process is swapped off and then brought back on, and this is called a context switch. So spin locks that were introduced in Progress 6.3 is a mechanism to influence the OS scheduler, to tell the OS scheduler, don't swap me off yet. I want to stay active. And until I run out of my spin tries, hence I couldn't get the lock I was trying to get, then yeah, it's time to swap me off. I gave up, swap me off this one, I'll reset my counter, bring me back on, and then I'll try to get that lock again for a spin try number. Everybody understand that what spin locks are? I was hoping that this is a crowd of DBA type people, so spin locks should be pretty review at this point. So the spin setting as it retries is just trying to influence the OS scheduler to determine how long it can stay on a CPU. So by default, with NUMA, your memory is going to be on a single node. You can change this. I don't know why you'd want to, but you can have a setting to set NUMA to say that memory is interleaved. So block 1 is on node 1, block 2 is on node 2, block 3 is on node 3, block 4 is on node 4, block 5 is on node 1, kind of like RAID. But that doesn't make much sense in the memory world unless you want everything to be slow. That would certainly be a way to make your environment slow. So that's not the default. The default is to allocate memory on a single node if possible. So if your memory let's say you have 128 gigabytes of memory on a node, and if your memory allocation is 64 gigabytes, it's going to try to allocate that on that single node. If your memory allocation is 130 gigabytes, and you only have 128 gigabytes on a node, it's not going to be able to allocate on a node. It's going to allocate the first chunk on that node, and then the remainder will be on the next node. So when we think about open edge memory, what's the majority of the memory? Dash big B, right? Each database block, hopefully 8K, is going to be on, dash big B is going to represent the number of 8K block units that are going to be there. But there's also other stuff in shared memory that's beyond dash big B. We always think that dash big B is all in memory, and in the scheme of things, it is all in memory, but there are really, really important pieces that are not dash big B that are in memory, and those tend to be allocated first. And there's LRU chains, latches for the buffers, BHT latches, and all the latches that if you go into Promon and look at all the latches, all those latches exist. All those latches are in shared memory. So latch allocation is first. This is important. So what you end up having is something that looks like this. Latches are up front, dash big B is after that. So does this help? You can imagine it will, right? So let's imagine that you're on a single node. Not a big deal. Everything fits in one node. So now you have all your memory, all your latches on a single node. It's a great way to be. It's like you're not on a NUMA machine, which is nice. And as an anecdote, we've had customers that have been on NUMA, and we've had to lessen the dash big B and disable NUMA, that their motivation for NUMA was memory, not CPU. As I said, you don't need 128 CPUs to run an open edge application, but they wanted the memory, and we disabled a NUMA node, just said it doesn't exist on the machine anymore. It lessened their memory, but life got better because they never had processors that ran on far CPUs, so there was never that far memory read. So this is that world. We're on a single NUMA node. But what happens if your big B is large enough that it's going to expand across a NUMA node? Well, there you go. So it's not the latches that end up expanding. It's just the database buffers that end up getting pushed to the other side of the NUMA node. What's that mean? Process on node 1, reading memory on node 1, fast. Process on node 1, reading memory on node 2, slow. Is that a big deal? Well, in the scheme of things, it's probably not, because the buffers are not really where all the work happens. The latches are where all the work happens. So majority of latches will be, if not all the latches, will be on the first node, or the node that you start on, right? So, and it's not guaranteed to be the first node, right? When you say ProServe dash big B, it's the process that gets assigned to. If that process gets assigned to node 2, then the memory is going to be on node 2. We have a question in the back?
Yeah, from the chat, someone is asking, is it possible to identify from a virtual machine if the virtual host is on NUMA, or do you have to be on the host to work that out?
So the question is, in the virtual world, is it possible to know in the virtual world if that VM is on a single NUMA node or not? And I'm going to say from the operating system, no. The operating system itself, so OpenEdge running on an operating system, it can't tell where that memory is. I'm sure there are NUMA commands, and this might be a good time to talk about Adam. Adam's doing a session at 5:30 today? 5:45 today about benchmarking, and one of the things he did was benchmark NUMA on bare metal and benchmark NUMA on VM. So I'm going to defer that question to Adam, because I don't know the answer on the VM control.
And VMware, you can also set the affinity of your entire VM to a particular node up there. So that's actually the easiest way to do affinity, is by using VMware. You can define each individual process at the operating system level, but you don't want to do that. It's very hard to do.
Okay, so I'm going to repeat what Adam said, which is kind of implying where I was going. In vCenter, in that world, you can define your VM to be affinity to a specific node. So that would be, and to Adam's point, that's a great way to guarantee that all your processes live on a node and all the memory is assigned to that node. And we've been saying this for years. Modern database tuning that Gus and I did years ago, we said, you have a NUMA machine, it's not great for OpenEdge, great for VMs. Make it an ESX, part of your ESX farm, slice it up, and then you now have a VM that's affinity to a node. So what am I saying here? So here we go. So the question is, and Adam alluded to this as well, is, okay, so now here we are, we're on a NUMA machine, not on a VM, but it's a NUMA machine, bare metal, or it's a NUMA machine. I had a VM that had multiple nodes in this NUMA machine as well. Can you cause OpenEdge or processes to be tied to a specific node that matches the memory? And that's what this question says, and the answer is yes. There's tricks to it, and I did some benchmarks to go do this. We had to go prove this for one of our large banking customers. They were on AX, and they ended up over-provisioning the machine, and it popped into a NUMA configuration on the AX environment, and things went bad pretty quickly. And what went bad were the latches timed out all the time. We'll talk a little bit more about that. But so that was the concern. They migrated from AX to Linux, and now knowing that Intel has the same issue, and it's even more exacerbated on Intel because of the 4 CPU limit, they were really concerned about NUMA. So I went and benchmarked this and played around to see if we could get affinity and guarantee that they would never have that far memory read that we're so concerned about. So the answer is yes, you can do it. And it's again with this NUMA control command. So NUMA control, you can use this to spawn your process. Instead of spawning the process directly, you can say NUMA control physical bind your process to your CPUs, 0, 2, 4, etc., and then launch _progress and all the parameters that go with it. And what this does is this binds this process to those CPUs. So when the scheduler swaps that process out, which is going to swap it out, it's going to context switch it. When it comes back on, it's guaranteed to be on the CPUs that you're binding it to. So how do you determine this? NUMA control hardware tells you which CPUs are on which nodes. In this example, and this is not always the case, you need to do this to know this, but in this example, node 0 had all the even CPUs and node 1 had all the odd CPUs. But that's not always the case. I've seen cases where it'd be 1, 4, 8, and so on and so forth. It's not always going to be an even odd swap. So you need to know what it is, and then you can figure out what you want to do. So in this case, we would NUMA control physical bind from 0 to 22, all even numbers for _progress, and that will bind this process to node 0. So all fun, but did it work, right? That's the question. So for lack of anything else to do, which is, I was talking to Adam just over lunch, and I'm glad I chose the benchmark I chose. I chose the ATM benchmark to do my test. Adam chose the exact opposite. I'm guessing you used reprobe, is that what you did?
We used reprobe.
So you're getting the update-only view of NUMA, and Adam's going to be giving you the read-only view of NUMA. So I used the ATM benchmark. Gus, my boss, wrote the ATM benchmark back in 1990, 1991, and it was based on the TP1 benchmark. So who's not familiar with ATM? Good, so I don't have to go in detail. But you know, there's accounts, tellers, not real world, one index, and if you need it, it's here. So it's a very easy benchmark to run. You build a database, and then you type go twice, and you're off and running. So as part of the go twice, I modified the go script to make this environment variable, NUMA opt. NUMA opt1, NUMA opt2 to physical bind thing, so I was kind of playing around with things. And then I set the clients to be Numa Opta 1 and the server to be Numa Opta 1. If I wanted to make things so they were bad, I'd put clients on Numa Opta 2 and server on Numa Opta 1. That would force all clients on one node and all servers on the other node. So I played around with this to watch things as they went on one node versus the other node. So I did the just let it be case, and then I did the let's bind it to a single node case. So I set these environment variables, and then I changed the do client do driver to include these, and we're off and running. So what's important here? Latches. That's really what's important. When any of our customers, any customer that we've seen at Progress, they cross the NUMA boundary, what's the indicator that they've crossed a NUMA boundary? It's latch timeouts. So so latches, for those who don't know, are regions in shared memory to lock structures, to protect code, saying I'm going to go do something and I can be the only one doing this at this time. So I need to have exclusive access to this memory. A lot of people confuse latching and record locking, and they're not the same. Record locking is locking a record in the database. Latching is locking a region of shared memory, so they're unrelated to each other. Conceptually, you could kind of think that they're the same, but they are unrelated to each other. With record locking, you could lock a record, and then you could pause and be waiting on user input, and that record's locked forever. With latches, it locks a latch, and there's no user intervention at all. There's no pause. It's going to go lock a latch, do what it needs to do, and unlock that latch. So, two things. One is if you're on node 2, locking a latch that's on node 1, just checking to see if that latch is locked is now 3 times slower. That's pretty bad. But worse, now you're on node 2 and you now have that latch locked, and now you're working on code that's going to be modifying memory, because that's the whole point of latches, and that memory's on node 1. The time you're going to hold that lock is 3 times longer. So that's going to cause all the other processes that are trying to get that latch to spin and latch timeout. So what's the result? Is you'll end up seeing latch timeouts in Promon. How do you see that? Promon, R&D, DEB, GHB, 6, the magic menu, and number 11 to go look at your latch timeouts. And if you see high latch timeouts, and high latch timeouts become very religious, going to give you my religion. You have latch timeouts more than 10 a second consistently, you have a problem. Other people think differently, but that's has been my tried and true measure. If it's more than 10 per second religiously, you got to change the application, you got to change something, because that's really high. But I'm going to show you some benchmarks, some graphs that show things that are really, really high. So in this case, our latch timeouts are 10,000, 8,000 per second. That's more than 10. So Houston, we have a problem, right? Left-hand side is NUMA, just out of the box. Right-hand side is NUMA with affinity. And what do you see that's different? It didn't look striking to me, so I had to go look elsewhere and found out that this benchmark was completely disbound. Completely, utterly disbound. So NUMA had no effect on it whatsoever, because we were latched on the MTX more than anything else, and the MTX is held over I/O to the AI and BI files, so it was useless. So what did I do? Because what was the goal of this? The goal of this benchmark was to test affinity. I didn't care about testing disk I/O. So anybody guess what I thought to do next? To get rid of disk I/O?
Memory disk.
No memory disk. Dash Big B was huge, but I ran with dash R. That gets rid of disk I/O, right? So here I am running with dash R, and I got to see what the benefit of NUMA was, and did this change affect NUMA? And you can see the difference here. So with dash R, our latch timeouts went from 6,000, 8,000 per second down to a much more reasonable, in some people's world, 250 per second. But with affinity, it dropped down to 150 per second, which showed that we had significant impact by using Affinity, because we're holding latches for a shorter amount of time, and when we're testing the latches, we're testing the latches more efficiently. So what's the true result of this? So these are transactions per second, the output of what the ATM benchmark gives you. There's a lot of things you could use as a measure, but this would be a measure. I mean, other things I looked at was how many creates per second, how many reads per second, how many updates per second. So I was looking at all that, but the TPS number is really what the ATM spits out, and 46% increase with using Affinity. Or you can look at this as a 46% performance penalty if you just let it go. So to add to this point, make it a VM and use that VM and tie that VM to a specific node, and then make another VM and tie that to another node and run two OpenEdge applications on it. Great, that's the way to do it. Another way would be to do what I did and use Affinity here. Gus?
Well, okay, so these are just numbers.
These are just numbers.
Yeah, they are. What's the true measure of success?
I know you know the answer to this. Are your users complaining? Yes, they're always complaining. Was that your point?
Yeah.
Yeah, okay. So Gus says these are just numbers. What's the true measure of success? Are your users complaining? I argue they're always complaining. If they're not complaining about performance, they're complaining about something else. But are they complaining about performance?
Are they complaining less?
Right. Could they see a difference? Right. And that's the key, is can they see a difference? And I can tell you from real world experience, and there's people in this audience that also have this real world experience, is when you cross the NUMA boundary, they know it. It's very obvious. And when you can get them not to cross the NUMA boundary, it's also very obvious. It's to the point of, in this one case with 8,000 users on the system, when they crossed the boundary, the application was unusable. Screens that would refresh in 2 seconds at the most were taking 2 to 3 minutes to refresh, if they refreshed at all, because most of the time as a character app, people were pressing Control-C because they didn't know what was going on. Okay, so we talked about all this stuff, and we're getting this increase. So how can you bring this home if you really wanted to do this? Well, one of the problems is if I start a process, and that process starts a process, let me give you a hint how this works. ProServe starts a process, and then guess what it does? It starts another process, and then it terminates that process to give you the prompt back. Then you connect a client session to it, client server, guess what that does? ProServe spawns another process. You connect an ODBC connection to it, guess what that does? ProServe spawns another process. So do you need to do this all the time? Well, once you bind a process to a CPU or a set of CPUs, all of its child processes will inherit that binding. So I was thinking, before discovering this, that I would need to go modify underscore mproserve on my machine to make it a script and have that do the NUMA control -fizbind my thing with underscore mproserve.exe or something like that to make things different. But you don't need to do that. But that was a thought in my mind to be able to deal with the client server aspect as well as the SQL Server 2 aspect. But it does follow. And so all these things are spawning processes. Okay, so that's where I'm at. 38 minutes in, I think I'm doing pretty well on time. So this is the first time you're hearing me say the words, NUMA's okay. Because up until now, NUMA has been a 4-letter word for me since 1996 to now. But we're kind of forced into this, so we have to take our heads out of the sand and deal with this issue. And it's not easy to deal with. VMware approach is a really reasonable way to deal with this, but if you can't do the VMware approach for whatever reason, then using this NUMA control fizbind option is a way to get past this. So if you're caught on this, there's a way to do this. What this does, however, is it's going to limit that big machine to a smaller set of CPUs, which may be okay. It's certainly better than the alternative of just turn off a node completely. If you turn off the node completely, you lose those CPUs, not a big deal, but you lose the memory that's associated with it, which might be a bigger deal. So if you need memory, and it's okay for that memory to cross a boundary, pin those processes to the node that started the allocation of the memory, and life will be better. So with Affinity, it will help. So at this point, I'll take Furgal. I had to go look that up today. This is Gus. It says ask. That's what it means. I know. Like, so if you go Google Translate and you say question, and then say what's it mean in German, it says Fragen. If you go in German and say Fragen and see what it says in English, it says answer. Or, no, actually not answer. It says ask. It says ask. I'm like, okay, ask. Any questions? Yes.
I have a customer who runs 4 databases on a single machine.
Yeah.
Let's suppose you move this to NUMA environment. Can we tell NUMA to start each database on different nodes?
For sure. Now, yes, for sure. So the question is, we have a environment with 4 databases, and it runs on a single machine now. Can we move this to a NUMA class machine with 2 or 4 nodes or whatever, and then pin each database and all the associated processes to that node? Certainly here with physical bind, you can do that. However, the caveat here is, how do the clients connect? Do the clients connect shared memory to all 4 of those databases?
No.
Perfect. Because if they connected shared memory to all 4 of those databases, where there's a lot of applications that are multi-database applications with a single schema across 4 databases in one application, it's very common. You could have a shared memory connection that runs great on node 1, and then node 2, 3, and 4, it's not running well. But if they're isolated atomic environments, sure, you can, node 1 gets database 1, node 2 gets database 2, node 3, node 4. Not a problem at all using the NUMA control physbind option. And that's a great use of a NUMA machine, because that now you're using, in my example, we were only using 1 node for CPUs. The other set of CPUs were doing whatever they wanted to. So doing this is a great use of node 1 CPUs are going to be busy, and node 2 CPUs are going to be busy.
And if you are using SOA and shared memory, you should use the same node for SOA agents and for the database buffer.
So the question here is, from a PAS-OE world, where should that be, I guess is the question. So PAS-OE is going to have its own memory, right? So PAS-OE is going to allocate its own memory, and that memory is client memory that's really only allocated to that PAS-OE instance and its threads that are associated with it. How is PAS-OE connected to the database? If it's client server, then PAS-OE can live wherever it wants to be. But if that PAS-OE connection is on the same machine and it's a shared memory connection, then that PAS-OE process needs to be bound to the same process where the server is. So it's all about that, that memory segmentation. Is memory segmented, meaning your client server, or is memory not segmented, meaning that you're shared memory? And if you're shared memory, you don't have segmented memory. You need to be near it. Any other Fragen? Okay, I'm going to finish by saying I found this interesting. I was pleasantly surprised by my results. I'm going to go see Adam at 4:45 today. I'm going to be even more pleasantly surprised at his results. Not to give too much away, but his are different than mine. And we'll see better or worse. Okay? Thanks, everyone.